Welcome to Scale Up University. Welcome to Probability for Machine Learning course. So this is the lecture 3 of module 2, and in this lecture we will discuss source of uncertainty 1. Like the first source of uncertainty, that is the noise in observations. So noise in observations is one of the source of uncertainty, and that is what we will discuss in this lecture. So just let us take a very brief overview of the lecture before diving into the core concepts covered in the lecture. If we talk about a common reaction when a model performs poorly, like let us suppose you prepared a machine learning model or a AI model and you found that its performance is very bad, its accuracy is bad, it is performing poorly. Performing poorly means it is making wrong predictions, it is giving wrong classifications. So that is what is meant by poor performance. So what we do is we blame data. We say that the data must be bad. So the data must be bad. Let's clean it more. And it is obvious also. Like if you think about it, we know that machine learning model data plays a very important role. Whatever the insights the data has, whatever the patterns the data has, the model will perform accordingly, the model will learn accordingly, and hence model will do the predictions accordingly. So definitely it is like it makes sense that data plays a very important role, and if the model is performing poorly, then for sure data must be bad. Like the training data which we are using, it must be bad. That's why we are not able to achieve a good accuracy. So what we try to do is let us try to clean it more. So whatever training data we have, so let us try to pre-process it more. Let us try to clean it more so that we increase the model's performance. But in reality, this is wrong. And that is what we will discuss in this lecture. This lecture will show us that why even good data produces uncertain models. So this is very, very important discussion we will be doing in this lecture. After this lecture, it will be very clear to you that even good data can produce uncertain models. And the core reason for that is the data will be having some noise, which is unavoidable. So there are some noise which is unavoidable. So the idea is no matter how hard you clean the data, yeah, like no matter whatever efforts you put to clean the data, there will be some noise that you cannot remove, that cannot be removed, that is irreducible. So noise has got some irreducible components that can never be removed from the data. So some noise is unavoidable, and hence we say that even good model, like even good data, can produce uncertain models because even the good data can have unavoidable noises. So some noise is unavoidable, and there are also some noise which is invisible. So hence noise plays a very important role. Noise in observations, noise in data. So when you are training a machine learning model, you will be using data, and that data will be having noise, and that data will certainly be having some unavoidable noise and some invisible noise, because of which no matter how like you clean the data, no matter whatever efforts you put to clean the data, there will be some noise present in the data, and hence the model will not be 100% accurate. There will be some uncertainty will be there in the model for sure. And hence understanding noise is very important, because if you understand noise in observations, it will help you to design, evaluate, and trust machine learning models. So understanding noise is very important, and that is what this lecture is about. In this lecture, in some good detail, we will be discussing the noise. We will be understanding the noise in observations, the noise in data, because it will help us to design, evaluate, and trust machine learning models. Because now it will be very, after this lecture, it will be very, very clear to you the significance of noise. You will understand that there will be certain noise which will be unavoidable, which will be invisible, and hence there will be uncertainty in the model no matter what. And then you will be mature enough to handle that uncertainty. Then you will be mature enough to not to try to eliminate uncertainty, but rather to deal with that uncertainty, to measure that uncertainty, to use that uncertainty to make some good decisions using the probability theory. So that is the significance of this chapter. So in this lecture, what all topics we will cover? So first we will understand what is noise. What exactly is noise? That we will understand. Then we will look into the difference between measurement noise versus process noise. Then we will talk about examples of noise in machine learning systems. Like we will discuss noise from the context of machine learning systems. Then we will also discuss how noise corrupts input features. So we know that in machine learning we have input features. Now how the noise can corrupt those input features, that we will discuss. And then we will be discussing why noise cannot be fully removed, because noise will be having some irreducible component, some unavoidable component, some invisible component which cannot be removed. So noise cannot be removed fully, that we will be discussing in some good detail. We'll get a clarity of it. Then in this lecture we will talk about consequences of noisy data in machine learning, like what consequences the noisy data can have, that we will discuss. And then one very important discussion we will make in this lecture, that is why models trained on noisy data must be probabilistic. Because once the noise is present in the data, there will be uncertainty. The output will become uncertain. The model will become uncertain, and hence the model has to be probabilistic because uncertainty is there. So that we will discuss in some good detail. Then we will talk about noise across data types. So from the machine learning context, noise across data types we will discuss. And in the end, we will conclude this lecture with the topic impact of noisy labels on model performance. So noisy label means wrong classification, because we label the data. And what if we do a mistake in that? So noisy label means a data point which is labeled wrongly, that we can call it like noisy labels. And definitely it will have a very bad impact on the model performance. So that all we will discuss in this lecture. So these all topics we will cover in this lecture one by one. So this is the module 2, that is uncertainty in machine learning, and lecture 3, source of uncertainty 1, noise in observations. So first we will talk about the first topic of this lecture, that is what is noise. So let's try to understand what exactly is noise. So basically noise is any random variation or error in observed data that does not reflect the true underlying signal. So noise is any random variation or error in observed data. So that observed data, it is having some variation or error from the true signal. So that does not reflect the true underlying signal. So we can say that if there is a noise, then the value you record is not equal to the true value. So whenever the observations or the value you record, if it is not equal to the true observation or the true value, it means definitely there is some noise in the recorded value. There is some noise in the observation. So that is the meaning of noise in the observation. So whenever there is a noise in the observation, the value will be different from the actual value, the true value. Whenever there is a noise is there, the label you store is not equal to the true class. Whenever the noise is there, the feature you measure is not equal to the true factor. So noise is basically any deviation from the true value. That is the noise. Now one very interesting thing about noise that you should know. See, always remember, noise is not malicious. Rather, It is a natural consequence of observing the world. So the idea is very clear. The idea is that noise is not something which came out of the box or which occurred randomly, or noise is not malicious, rather it is inherent. Like whenever you are observing the real world, there is high chance that you will make mistakes in observing the real world. Rather, like you can make mistakes via the measurements, like the instrument, your instruments might be wrongly calibrated, they might have some internal errors, or there might be some human errors. There are many factors because of which the observations might have noise. The observations might be slightly deviated from the true value, and that is the noise. So noise is not malicious. Noise is a natural consequence of observing the world. And when you are building machine learning systems, when you are dealing with machine learning systems, you have to deal with the noise. Noise is something which will be there. So you have to deal with the noise while dealing with the machine learning system. For example, let us suppose there is a temperature sensor data is there. Like we have a temperature sensor. It can sense the temperature. Now this temperature sensor, let us suppose it measured some values like, so let us suppose the true temperature is 25 degree Celsius, and let us suppose the recorded value. So suppose we got 24.8, 25.3, and 25.1. So if you look at the recorded value, they all are slightly deviated from the true value. So the true value is 25, but the temperature sensor, they measure 24.8, they measure 25.3, they measure 25.1. So we can say that noise is there in the observation, and that is the noise in observations. The noise is there in the observation. So here the environment did not change. So the environment did not change, rather the measurement did. So what happened is the environment was fixed with 25 degree Celsius as the temperature, but we had different measurements for the same environment. And that is what is leading to uncertainty. So whenever there is a noise, there is an uncertainty, because the true value is 25, but the recorded value is slightly deviated. So 24.8, 25.3, 25.1. So so definitely there is a noise in the observation, and that noise is leading to uncertainty. So we can say that one very interesting point we can make: noise is uncertainty injected at the moment of observation. So here at the moment of observation, the true value was 25, but noise was injected because at the moment of observation, the sensor observed it to be 24.8. So the noise was injected. 25.3, the noise was injected. So, and the like noise is uncertainty which is injected at the moment of observation. So whenever we are measuring, whenever we are observing the world, then definitely we are injecting the noise. We are injecting the uncertainty, and noise is the uncertainty. So with this, all this discussion, one very important point we can say is that, very important point, what the model sees is not reality. Because see, what the model is seeing, that data will be having noise in it. So the observations will be slightly deviated from the reality. So what the model sees is not the actual reality. Rather, it's a noisy shadow of reality. So one very important observation we saw. So now it is very clear to you that whenever a machine learning model sees the data, it is not seeing the actual reality, but it is a noisy shadow of reality. Noisy shadow of reality means that data will be having some noise in it. So it will be a noisy shadow of reality. So now we will discuss the next topic of this lecture, that is measurement noise versus process noise. So we have to discuss measurement noise versus process noise. If we talk about measurement noise, so measurement noise is the noise introduced by sensors, instruments, data collection tools. So here the process is stable, like there is no wrong with the process. The process is stable, but the measurement is imperfect. But if we, so this is very clear that there is no wrong with the process. The process is stable, but the measurement in itself is imperfect, because measurement noise, the name itself is telling, when we are measuring the data either via sensors, via instruments, or via data collection tools, that is the source of noise. So here the measurement is imperfect, the process is stable. Now if we talk about process noise, so here the noise is not introduced, rather noise is inherent in the system itself. So here the noise is inherent in the system itself, like the noise is the part of the system. Noise is not introduced from the outside world, rather noise is the part of the system. For example, human behavior. Now in a process, definitely humans are involved and humans can make mistakes. So human behavior can introduce noise. Biological processes, economic systems, so they may contain noise which is the part of the system itself, and that is the process noise. Now one very interesting observation about the process noise: even perfect sensors can't remove this noise, because this noise is something which is the part of the system itself, which is the inherent part of the system. This noise cannot be removed. Like, this noise can be removed via some major changes in the system itself. Perfect sensors can't remove this noise. If we take a real world example, if we talk about a fitness tracking app, so here the measurement noise would be step counter errors. So the sensors responsible for counting the steps, step count, it might have some problems. It might cause the error. So that's a measurement. Here measurement error is there, na measurement noise. And process noise is human behavior. And here human behavior means same person walks differently every day. The same person will walk differently every day. That is a process noise. So it's like the human behavior. And why it's a noise? Because of that there will be ambiguity. The model will not be able to determine the actual behavior, actual walking patterns of that person, because every day the same person is walking differently. So the model will never get to know what is the actual walking pattern. So here a noise is there, and that's a process noise. So in this fitness tracking app, we saw the example of both measurement noise and process noise. So we can say that one very interesting thing we can say, some noises comes from how we measure. Like some noises comes from how we measure, and there are some noises which comes from how the word behaves. So now it's very clear to you that measurement noise is about how we measure. Like the noise is introduced, it depends on how we measure. And process noise depends on how the word behaves. Like any external entity behaves, like human behavior. So if in a system a human being is involved, the behavior of human might introduce process noise. Or in an economic systems, like the supply chain, like there are many factors which might introduce the process noise. So now very important discussion we did, difference between measurement noise. See, measurement noise is easy to understand. Like, okay, whenever you are observing the real world, any measurements you are doing, like you're collecting the data via some tools, some sensors, that's, and in that if any noise is there, that's the measurement noise. But apart from measurement noise, we can also have process noise. And this is very crucial because if you are building a machine learning system, you have to be very careful whether you are introducing a process noise within in the pipeline or not. Because in the pipeline, there might be a chance that you might be introducing some sort of process noise, and we have to identify that. Okay, now we'll discuss the next topic of this lecture, that is examples of noise in machine learning systems. So if we talk about examples of noise in ML systems, we have sensor noise. So as the name suggests, like sensor noise is the one which is introduced by the sensor itself. And when I talk about sensor, I may refer to cameras, like the camera grain. I may refer to microphone, IoT sensors. So these are like sensor and many more. Like the noise introduced by the sensor is the sensor noise. So there are so many different types of sensors. Now, if we look at one real world example of this sensor noise, we have, so in computer vision, a face recognition model, it sees light changes due to the sensors. That's the camera, motion blur. So it is not able to capture the motion clearly because of the limitations of the camera, and some sensor artifacts. So these are like some real world examples of sensor noise, which is introduced by the camera when you are trying to recognize a face. So when you are trying to capture a face, either the video or the image, you might have some noise. And because of that, what will happen is that every time the face is captured, the face will be same face. But because of the noise, every time it will lead to different pixel values. And hence it is introducing a very high level of uncertainty, ambiguity, because the same face is having different pixel values. Like the first time you took the face, you are having a training data. Second time, the training data is different. The third time, the training data is different because of the sensor noise. And it's very common in machine learning. So this was sensor noise. Then we have human labeling errors. So as the name suggests, human labeling errors, what it means is that, see, always remember, like in the training data, it's the labeled data. Like every data point, like we label it and humans label it. Now humans might make mistakes. We call it human error. They might make mistake because of some pressure, some time constraint, some confusion, some incomplete context. They might make mistake. And that mistake in labeling is the labeling error, human labeling error. Now, if we talk about an example of it, human labeling error, that is sentiment analysis. Sentiment analysis. So in sentiment analysis, let us suppose I have a sentence called that was sick. Now this same sentence can be labeled differently. Like it can be labeled as negative. It can be also labeled as positive. So the same sentence was labeled as negative and positive. Now one very important point to be noted, like it's a very core concept. Label noise introduces irreducible uncertainty. Now, what is the meaning of it? Let us try to understand. Now, see, the idea is that when a label noise is introduced, then definitely the model will get confused. Because, see, machine learning model, what it is doing, it is learning patterns. It knows that, okay, if this is the input, this is the output. So, it learns the mapping that, okay, for a sentence to be a positive sentence, this should be the sentence. Like, this should be the pattern. So it learns like that. Now, if you label the training data wrong, like if the label noise is there, then what will happen? The training will go wrong. Like machine learning model will misinterpret. It will learn the patterns in a wrong way. And And this is something which cannot be corrected. Like label noise, it will introduce an uncertainty that is irreducible. Irreducible means once the model is trained wrongly, we cannot undo that impact. We cannot undo the effect. I hope it is making sense. But sensor noise is reducible. S- Sensor noise is reducible uncertainty. What it means is that, see, we already saw because of the sensor noise, what is happening is that same training data is like slightly deviated, and we can undo that effect. How we can undo that effect is that if we collect lots of samples, like if we talk about face, if we collect lots and lots of sample, then statistically we can eliminate the noise, because with every sample the noise will be there, but the other sample will have some reality. For example, I'll tell you one example, like I'll try to explain it clearly. Like let us suppose I have a face, like very rough diagram I'm making just for understanding purpose. Now let us suppose there is some noise present in this region. So we don't know the real pixel values for this region. Now in the second image of the same person, we might get the true pixels for that region, and in that second pixel, maybe the noise may be somewhere else, maybe here. So what is happening is that so if we are able to collect lots and lots of samples, then automatically we will be able to determine the true pixel values, because in this sample definitely we are not sure about this region. These pixels are like deviated from the true value. Some noise is there, but the second sample of the same person will tell us, okay, these are the real pixel values. So we got the reality. So in this way, if we get lots and lots of sample, and via statistical estimation, we can get the complete picture of a human, of a face with minimal noise in it. And hence we say that sensor noise is reducible uncertainty. We can undo the impact of it, provided we increase the training size. And hence in machine learning, it's very common when you are doing supervised learning. It's said that you should have lots and lots of data, because with lots and lots of data, despite of sensor noise, you are able to reduce it, and that's the something very interesting. But if human labeling error is there, then no matter what, like let us suppose out of 1000 samples, in like 10 samples you made a mistake. Now if you make that 1000 sample as 1 lakh sample, then also its impact of those 10 wrong labels will be there, it will exist, because the model got trained wrongly. So that's why label noise is irreducible. Now the next example of noise in ML system is data recording issues. So we know that we use like data for data recording, for capturing the data, we might use some tools and all that. So there might be a scenario that there might have be some missing values. We are not able to capture the all the data. Like some features might be missing for a particular observation. Like in a particular observation, we had to capture 10 features, and we are only able to capture 5 features. So that is missing values. Truncated logs we can have. So this incomplete data, some rounding errors, and also wrong units. So all this might introduce some sort of noise in the machine learning system. If we take one example, real world example, if we talk about transactional data, so there might be instances wherein price is recorded as 999 instead of 9.99. There might be missing timestamps corresponding to transactional data. There might also be currency mismatch. So these small errors might definitely be there, and these noise this data recording issues. So data pipelines, they silently inject this noise in the ML system. So data pipelines inject noise silently. So silently means we will not at all get to know about the noise, because silently, that because the data pipeline will be providing the data for the machine learning model, and in that data itself these errors might be introduced, this noise might be introduced, and then it will definitely affect the machine learning model. Okay, now we'll discuss the next topic of this lecture, that is how noise corrupts input features. So if we talk about feature corruption, so the noise, it distorts feature values, it blurs decision boundaries. So because of the noise, feature values will get distorted, decision boundaries gets blurred, and it also creates overlap between classes. So we can say that what noise does is that noise turns clear boundaries into fuzzy regions. So let us try to understand it more clearly. Like, let us suppose I have feature 1 and feature 2. So these two features are influencing any target variable. Now let us suppose feature 1, it is taking values in the range 1 to 100, like this. Like range is 1 to 100. And let us suppose in the feature 2 the range is 1000 to 10,000, like this, for example. Now what happens if in feature 1 we get a noise of 5,000? It's a noise. Noise means some error, some deviation from the actual value, because we know that for feature 1 the actual value has to be between 1 to 100, but we introduce a noise 5,000. And for feature 2, let us suppose we got a value that is 50, and we know that it's a noise. Why it's a noise? Because we know that for feature 2 it should be a value between 1000 to 10,000. Because of that, what happened? Because of the noise, first we like feature values, it got distorted, because we have some observations which are away from the actual reality, which are not even following the constraints. So that thing is evident from this example. And also it creates overlap between classes, because initially feature 1 and feature 2, they were fully independent, they were totally independent, but because of the noise we introduced overlap between these two features, and because of this overlapping we blurred the decision boundary. Because when machine learning model was learning the pattern, it was very easily, it was able to learn that okay, for feature 1 the number has to be a 2-digit number or a small number. Machine learning model will very easily, it can learn that pattern, and for feature 2 it can learn the pattern that okay, it has to be a larger number, a 3-digit number or a 4-digit number. But because of the noise, even the model will get confused and we are blurring the decision boundary. So that's the idea. So now I hope it is very clear to you that whenever a noise is introduced, noise corrupts the features, and it corrupts to such an extent that decision boundaries gets blurred, because of which we introduce uncertainty. And because of feature corruption and because of the noise, so noise forces models to be probabilistic. So that's the idea. Because of the noise, uncertainty is introduced. Why uncertainty is introduced? Because the decision boundary got blurred, a confusion got introduced. Because of the blurring of the decision boundary, the prediction will not be done with full confidence. So uncertainty will be there, the predictions will be uncertain, and hence the model will become probabilistic. Instead of predicting the results or the outputs with high confidence, it will be predicting with some sort of confusion. Uncertainty is introduced, and hence the model will become probabilistic. So noise forces the model to be probabilistic. So that's the idea. Okay, now we'll look at the next topic of this lecture, that is why noise cannot be fully removed. So earlier we saw one example wherein we saw the example of irreducible noise, and that was labeling noise. Like if we make a mistake in labeling the data, then that noise is irreducible. So if we talk about noise, noise has both reducible component and irreducible component, and because of the irreducible component of the noise, noise cannot be fully removed. Now there is a common misconception that with enough pre-processing, noise disappears. So the idea is that, okay, I have the data. If I put best efforts in cleaning the data, if I do the pre-processing very properly, then the noise will disappear. But that's wrong. And why it's wrong? Well, let's see that. So if we talk about reality, some noise is unobservable, some noise is intrinsic, and some noise only appears later. So the idea is that despite of your best efforts in pre-processing the data, there will be some noise which you will not be able to identify, and hence it will be the part of the data itself. You will not be able to remove it. Some noise will be inherent, it will be intrinsic. It's not possible to remove it. And some noise will appear later. Like during the data pre-processing phase, that noise might not appear, but later it might appear. So because of these reasons, we cannot fully remove the noise. If we talk about one example of medical diagnosis, so in medical diagnosis example, we have seen that even with best doctors and best tests, diagnostic uncertainty still exists and biological variability will exist. Meaning to say that one very interesting thing I'll discuss with you. It's a real world example we are discussing medical diagnosis. So in medical diagnosis, despite you are having best doctors, despite you are doing best test with some state of the art instruments, still you cannot claim your diagnosis to be 100% accurate. Still uncertainty will be there. Chance is associated. So even with the best doctors and best tests, diagnostic uncertainty will exist, and biological variability is something which is a process noise. Biological variable is something which is a process noise. So here there might not be any measurement noise because you are using the best instruments. But despite of that, biological variability might be there. And what is this biological variability? Like let us suppose based on the test results, whatever uh, observations we saw, it is applicable for 10,000 people, for example. But there always exists one rare case. For him, the diagnosis has to be different because of a slight biological variation. And such rare cases exist. In real world, they do exist rare cases which have got some special kind of biological variability. Because of that, the diagnosis which is applicable for thousands of people with the same set of test results, same set of symptoms, is not applicable to that person. So this rare case and this other set of people, they both had same test results and they both showed similar symptoms. Despite of that, because of certain biological variability in that rare case, the diagnosis is not applicable to that rare case. And it is introducing uncertainty. So the reality is somewhat very different. So here it's a process noise. This biological variability is a process noise. And because of the process noise, whatever the machine learning model will make the predictions for this rare case, that will be different. Because for that rare case, that prediction is not applicable at all. That prediction might be applicable for thousands of other people with the same test results, similar symptoms, but it is not applicable for that rare case. So we can say that cleaning reduces noise, but it does not erase it. So the idea is very clear. If you're putting best efforts in pre-processing the data, cleaning the data, definitely you will be reducing the noise, but you cannot erase the noise because there has to be some noise. like some noise might be unobservable, some noise is intrinsic, like the process noise. Like here in medical diagnosis example, we saw the example of intrinsic nature of the noise. Some noise may appear only later. So cleaning will reduce the noise, but it will not erase it. Okay, now we'll discuss the next topic of this lecture, that is consequences of noisy data in machine learning. Now see, because of the noisy data, what will happen? We will have variability in model predictions. Now what is this variability in model predictions? Let us understand. With the same input, we are getting slightly different outputs. And why is it so? Because of the noise in the data. Because of the noise in the input, the machine learning will be learning some, like machine learning model will be learning some noisy patterns. And because of that, the output will be slightly different. So same input, but here we know that input with the noise. For example, if we talk about face recognition model, like you took three images of the same person. Now definitely those three images will be slightly different now, because of light conditions or some other environmental conditions. So despite these three images belong to the same person, they will be having some measurement noise, some noise will be there, and because of that the output will be slightly different. And how the output will be slightly different? Let us suppose these three images belongs to John, the face of John. Now the prediction will be John, but the probabilities will be different. So this image will be predicted as John with a probability of like 97%. This will be like 92%, and this will be like 85%. So more the noise, more the uncertainty. So the confidence level will decrease. So for the same input, because here the input is same, all the images belongs to the John, but the output is different. So that's the variability in model prediction. And the second consequence is overfitting to noise. Now, what is overfitting to noise? Let us understand. So the machine learning models, they may learn noisy patterns, learn from random fluctuations, noisy patterns. And one very important point, models may mistake noise for signal. Like, like what model might do is that model might start considering the noise as signal, and it starts learning those patterns, and hence the models will get confused. So model may start learning noisy patterns, and if it is so, then the model will be confused and it will become more and more uncertain. Now it has been seen that with small data sets, like you are already having a very small data set, and that too is very noisy, like it is having lots of noise. So this small data sets plus you're using a complex model. So small data sets plus complex models will lead to overfitting. And in overfitting, what will happen? You will get training accuracy as 99%. Like while training the model, it will give you very good results. But in reality, when it comes to validation, so validation accuracy will drop. It will be just 65%, for example. And here we say that it's overfitting. Why it's overfitting? Because see, what has happened is that the small data set you used to train the model, it was already noisy. It had s- significant amount of noise, and unfortunately the model learned the noise. Because of that, the, the training was not efficient. The model did not learn the actual signal properly, rather it learned the noise. And because of that, when it was exposed to new data, which was like original signals and not the noise, it gave a validation accuracy of just 65%. So whenever such thing happens, like when that in the training you are getting a very good accuracy, but while validation the accuracy drops, then definitely it is the case of overfitting. And overfitting means your data set has got noise, and you have to work around with the noise. to overcome the overfitting. So we can say that overfitting is basically memorizing noise. And memorizing noise, when it will happen, when in your data set you have a significant amount of noise, the data set is small. In that scenario, your model will start learning noisy patterns, random fluctuations. And once it will do that, then the learning is not good and overfitting will happen. Now, the one more consequence of noisy data in machine learning is bias variance implications. So we know that. So see, one very important observation you should know: noise increases variance. See, what is the meaning of variance? Variance means drift from the actual value or drift from the mean. So let us suppose you have a feature, you have a feature one. Now this feature will be having some values and some average value will be there, average of this. So variance is the drift from the average. So higher the variance means for that particular observation, the drift from the average is very high. It means it is an outlier or it is a observation which is showing some different trend. It means definitely there is some noise associated with that observation. So high variance. So noise increases variance. So high variance is an implication of noise. Models must trade. So there's a trade-off between sensitivity to data and stability of predictions. So that's the bias variance implications. So what happens is that see, when the noise is introduced in the data, so the sensitivity of the data will decrease because the quality of data will decrease, and because of that, predictions will get affected. So it's now very clear that noisy data has got some very bad influence on the machine learning systems. That is what we saw. Okay, now we'll discuss the next topic of this lecture. That is why models trained on noisy data must be probabilistic. So see, this is very clear to you that noise in the data will introduce uncertainty. So we can say that deterministic outputs fail under noise. So whenever noise is introduced, uncertainty is introduced, and uncertainty means probabilistic output and not deterministic output. So deterministic outputs fails under noise. So because of the noise, single correct options does not exist. Single correct output does not exist. Because of the noise, confidence varies. So we can say that probability is the only honest response to noisy data, because noisy data will introduce uncertainty and hence the output has to be probabilistic. The model has to be probabilistic. So probability is the only honest response to the noisy data. Okay, now we will discuss noise across data types in machine learning context. So we'll talk about different types of data and the noise associated with that. If we talk about images, we have lightning conditions. Because of the lighting, noise will be introduced. Blur. So these are the noise for images. Compression artifacts. If we talk about text, we have ambiguity in the text as the noise. We have sarcasm as the noise. We have misspellings as the noise. If we talk about time series data, then we have sensor drift as the noise and random shocks as noise. If we talk about tabular data, we have missing fields and recording errors as noise. So we can say that noise is universal, only its form changes. Now we will discuss the last topic of this lecture, that is impact of noisy labels on model performance. So if we talk about the impact of noisy labels on model performance, So we have, so noisy labels directly corrupts the learning signal. Noisy labels directly corrupts the learning signal, because of which it limits achievable accuracy and it creates uncertainty floor. It introduces uncertainty. If we talk about a real world example, I think you all are familiar with ImageNet data set. Now it's like a very popular data set. So even this ImageNet, it contains mislabeled samples and hence it imposes accuracy ceiling. Like because of the noise in the data, there is a upper limit to the accuracy. So the accuracy ceiling is there. So even famous data sets like ImageNet, it contains mislabeled samples. It has noise in it. So we can say that label quality plays a very important role. Label quality decides the maximum performance allowed. So maximum allowed performance, it depends on label quality. So label quality plays a very important role. So now we saw the impact of noisy labels on model performance. So finally we completed this lecture. So in this lecture we discussed in some good detail about the noise, and we saw that noise is unavoidable in machine learning. We saw that noise comes from measurement, that is the measurement noise, and it also can come from process, that is the process noise. We saw that noise corrupts features and labels, and we also saw that because of the noise introduces uncertainty, and because of that machine learning models become probabilistic and not deterministic. So noise makes models probabilistic. And one more very important point to be noted is confidence matters more than accuracy alone. Like whenever the model is predicting, the confidence is very important. Like it is predicting with like 50% confidence, 70% confidence, or 90% confidence. So that plays a very important role in machine learning. So I hope you got a good understanding of the concepts which we discussed in this lecture. So do subscribe to our YouTube channel, Scale Up University, for such interesting lectures and courses. Do share it with your friends, this lecture. Thanks for watching. Thanks for your time.